Okay, so thank you very much to come today again. So today we are going to do functional analysis, and we are going to solve the midterm of the academic year 2024-2025, the session of 3 February 2025. Functional analysis. Academic year 2024 with 2025. Okay, so the instruction here is to submit only one sheet, to write your name and your surname, your matricula. So it's not important. So our name here is functionalism. Our matricula is 2024-2025. So what is the first question? If you don't have the subject, let me write the entire question. So let omega a subset of Rg be a measurable set, and let Fn from omega to R be a sequence of measurable functions. What is the first question? The first question is to define the LP space and its norm. So let us define the space LP of omega and its norm. Okay. Now, when P is finite, so LP of omega, it is the set of measurable function such that an integral over omega of the absolute value of f raised to power p dx is less than plus infinity. So this one is the LP space. So we have the LP space. Now, if P is plus infinity, what is LP? So L infinity, it is the set of measurable function such that the essential supremum of the absolute value of f is finite. So what is the definition of the essential supremum? So it's the smallest m positive such that the absolute value of f of x is less than m almost everywhere. This is what we call the essential supremum. Now, what is the second? The second, okay. We say explain what it means for Fn to be converged in LP. So let us explain.
Romary, you didn't define the norm.
Oh, thanks. Grazie mille. Now the norm. So we are going to take the two cases. Maybe it is better for me to put the norm under the definition. Now, what is the norm here? The norm of f in LP is the integral in omega of this quantity all power 1 over p. So that is the norm of f in LP. And here, the norm when p is infinite, so when p is not finite, the norm is exactly the essential supremum of f. That is the norm. And the essential supremum is defined as the infimum of m greater than 0 such that the absolute value of x is less than m almost everywhere. Yeah. Next question. So, let us explain what it means for Fn to converge in LP norm. So, if we take f like this, a measurable function, measurable, Fn converge to f in LP norm if and only if the norm, the LP norm of Fn minus f tend to 0 when n tend to plus infinity. So this is equivalent to, the integral in omega of the absolute value of Fn minus fx raised power p dx tend to 0. That is it. So that is the definition of convergence in LP. So the second question is, if we take omega equal to R and we the sequence, consider the sequence fn of x equal to the indicator function of 1 over n 2 of x, or the characteristic function in the interval 1 over n2. So we are going to write it again. We know that this one is what we call a piecewise sequence or a piecewise function. So f1 of x, which is equal to the indicator function or the characteristic function, is 1 if x is between 1 over n and 2, and it is 0 otherwise. So that is the definition of this sequence. So the first question is to know or to check if fn converge almost everywhere. So let us check if fn converge almost everywhere and determine the limit function f. So to answer this question, you just have to check the limit, if that limit exists. So if the pairwise limit exists, so what is the limit of this quantity? So the limit of fm the limit of fn of x, so we're not going to think too more. You know that if x is between this interval, when n tends to plus infinity, so this interval is going to become the interval 0, 2. You can see, so it is 1 if x is between 0, 2, and it is 0 otherwise. So this is f of x. Nice. So we see that how it is easy. Now, the second question is, for which values of p does fn converge?
Romar,
Yes.
please. I thought that it was two questions, but
Yeah,
your answer just showed one question. You just answered one question,
the
the
question
limit.
was, does fn converge almost everywhere? Determine the limit of f, the limit function f. Yeah, they changed that. If you can find this limit, it means that the sequence converge almost everywhere, right? If you can find this limit, it means that the sequence converge almost everywhere. I read together.
I thought that we could, I don't know, uh, show that the function is increasing, for example.
To conclude what?
That the function converge almost everywhere.
That one is the strong convergence maybe that you want to do. You just want to check the almost everywhere convergence. Convergence almost everywhere, it means that uh, the function converge does not converge on a negligible of the function does not converge in a negligible set. That is what we call converge almost. So the function converge almost everywhere except on a set for which we have the measure equal to 0. That is the definition. And
Okay.
when you can compute this limit, you can directly conclude that the sequence converge almost everywhere. So you just have to check if this limit is possible, exist. So um, let us let us find the values of p such that fn converge to f in LP. So you know, uh, saying that fn converge to f in LP, it means that the LP norm of fn minus f tend to 0 as n tend to plus infinity. And what is this? So it means that the integral of the absolute value of fn this tends to 0. Now, what is fn? What is f? So this is just the integral on 1 over m 2 of the absolute value of 1 minus 1 over p gx. So this one is very easy. Then for all p and fn converge in LP to f. So there is no condition here. So you can see that whatever the value of p, fn is going to converge in LP to f. Fn converge maybe to f in LP. So the second question is to state the Beppo Levi or the Montone convergence theorem. So let us state the Beppo Levi or the monotone convergence theorem. The monotone convergence theorem. So I'm not going to write it today in red. So let Fk from Rn or from Rg to 0 plus infinity be a sequence of measurable functions. Or maybe you can directly say let Fk from Rg to 0 plus infinity be an increasing sequence of measurable function. You can say it like this. Now assume that Fk of x is less than Fk plus 1 of x for all k in n. And we have to assume this for almost every value of x. So almost everywhere. Then, so when you have this, so when you have a sequence of measurable functions, so if the sequence is an increasing sequence, then there exists f from Rg 0 plus infinity measurable such that the initial sequence, so the sequence that we have, Fk converge almost everywhere to F. And the limit of the integral of Fk is x is equal to the integral of f dx. So as I used to say, this means that when you have those conditions which are satisfied, you can switch the position of the limit and the integral. Since that as you have f here, what is f? F is the limit of fk when k tends to plus infinity. So this term is just there to say that we can switch the position of the integral and the limit. So maybe you want to compute the limit of the integral of a sequence. As it is not easy for you maybe to compute the integral. So you cannot have the exact expression of that integral. So you need to check if you can apply the Beppo Levi theorem or the monotone convergence theorem. So that is the theorem. Now, the second question is, consider Fn from 0, 1 to R. So where n is an integer and Fn is defined as follow. Fn of x equal to sine square of x over n plus 1. So the question is to use the Beppo Levi to compute the following limit. Let us use the Beppo Levi theorem to compute the following limit. So the limit when n tends to plus infinity of the integral between 0 and 1 of Fn of x dx. So you know what we need to check. The first thing is to check, is this sequence measurable, positive? Of course, you have to check this. Don't forget this. This means that the sequence of functions should be a positive sequence. Of course, sine square is positive, n plus 1 is positive. So the quotient of two positive functions or two positive number or whatever is still positive. Then we don't have any problem with the positivity. This function is continuous on 0, 1. So Fn of x, so sine square of x is continuous in 0, 1. So it is measurable. Since that when you have a continuous function, it means that your function is measurable. Now, the best thing to check now is the monotonicity. Does this sequence increase? That is the question, and you have to check it now. And the monotonicity is to respect to the index. So it's not respect to x. It is respect to k, or our index here is k. It is n. So in the definition, the index was k. So that is why I said k. Now our index is n. So we have to compute Fn plus 1 and compare Fn plus 1 and Fn. Fn plus 1 of x is what? It is sine square of x over n plus 2. Fn of x is sine square of x over n plus 1. Now it is very easy to compare this. Since this one is less than this one, so 1 over n plus 1 is less than 1 over n. This implies that sine square of x over n plus 2 is less than sine square of x over n plus 1. So then fn plus fn of f of n plus 1 of x is less than fn of x. So this means that fn, it is a decreasing sequence. Then fn is a decreasing sequence of measurable functions. The question is to know, can we still apply this theorem? Because it was mentioned that we need to apply it. Now, according to you, is it possible to apply it? You don't know.
Question again.
What?
The question again.
Now, we have a decreasing sequence of measurable functions. The question is to know, can we apply the Beppo Levi theorem?
No.
No, we cannot apply the Beppo Levi theorem in this case. But I don't know why. The question was to compute this limit by using the Beppo Levi theorem. It is a little bit strange. I hope that uh, I hope that my theorem is true, because I hope that I didn't do any mistake. I hope that we are supposed to have an increasing sequence.
What did you say?
I say that one of the hypotheses of this theorem is to have an increasing sequence. But now, as we don't have an increasing sequence, is it still possible to apply this theorem, since that Fn is not an increasing sequence? And the problem is that
I don't think so.
and the problem is that the lecture say that we should compute this limit by using the Beppo Levi theorem. I don't know why, but now we cannot use it. So we can use the Beppo Levi's convergence theorem. Now let us check if we can compute directly this integral. So computing directly this limit means to compute directly the integral. So what is the integral between 0 and 1 of sine square of x over n plus 1 in the x? So you have to linearize the sine square, and you have to know some little trigonometric. In trigonometry, sine square is nothing else than 1 minus cosine of tx over 2 dx. So you should know this. Now it is easy to find the integral of this. So the integral of this is x minus half of sine of 2x. So when we replace by 1, we have 1 minus half of sine 2 1 minus half of sine 2 minus 0 plus 0. So that is all what we have. So the limit of the integral of fn of x dx when n tends to plus infinity, it is the limit of the integral of sine square of x over n plus 1 dx when n tends to plus infinity. And this integral is what? So this integral is 1 over 2 over n plus 1 times 1 minus half of sine 2. When n tends to plus infinity, this is 0. And then this limit is 0. And you can see that the Beppo Levi Theorem does not work here again. You can see it. Imagine you just have to compute this one. If you compute the limit of this of fx dx, sorry, if you compute the integral of fx between 0 and 1, you're not going to have 0. This integral is what? So let us see what is fx. Oh, sorry, the fx is the limit of, let us find the limit of this sequence. What is the limit of fn of x dx? So what is the limit of sine square of x? What is the limit of this? This limit is always 0. So it is 0. Okay, 0. Yeah. We can apply the theorem, but we still have so just this is just a coincidence. It's not because of the theorem. So we still have the final result, but the hypotheses are not satisfied.
But f of x is 0 and 1 now.
No, it's not f of x. It's not the same. It is not the same function. That is the confusion that I was doing. This one, fn is
Oh,
1, 0 for this sequence. Now for this new sequence, the limit is just 0. So in logic, we see that you can have a false hypothesis, but you have a true conclusion. So this can be true, even this one is false. It's possible in logic, but it doesn't have any sense.
Sure.
Yes.
I think in the note he gave one example where the function was decreasing, but he continued to use the Beppo Levi.
How?
He defined a sequence which was equal to f1
Negative.
minus fk.
F1.
I didn't understand that part, but he defined a sequence which was gk is equal to f1 minus fk.
VK.
Yes, g.
Okay.
Small
GK.
g, like a sequence small g is equal to f1 minus fk.
F1 like this.
Yes, like this minus fk.
Minus FK like this.
Yes. But I didn't understand that part too. But
Okay, f1 minus fk. Okay, now you have to check to understand maybe the idea. When you have f1 of x minus fk of x, you have to check if this one is firstly positive. That is the first chain. Now, we can say that we know that, what do we know? This is just a parenthesis. We know that this sequence, fk, this is a decrease sequence. This is one is a decrease sequence. So fk is greater than fk plus 1. And we know that f1 is also greater than fk. I hope you understand. Since that the sequence decrease, since fk is decreasing. So if you have if you have a sequence, a decreasing sequence, it means that maybe fk so is less than fk minus 1, is less than fk minus 2, is less than up to, I don't know, f1. If f1 is the first term, so it means that f1 is greater than fk, right? I hope you understand.
Yeah, I understand.
So it means that if fk is less than f1, it means that f1 minus fk is greater than 0. That is the first thing to check. Now, we have to check the monotonicity of GK. And the idea was very smart because we are going to notice now GK is going to satisfy the Beppo Levi theorem. And the limit of GK is going to be the limit of this minus, the limit of GK is going to be the limit of F1 minus the limit of FK. And by this, we are going to have the limit of FK. Okay, let us proceed. We are going to apply the concept in this case. And maybe that is how you are supposed to do. Thank you for the idea. Now, since that we have now our sequence GK, what is GK plus 1? GK plus 1 of x is F1 of x minus what? Fk plus 1 of x. And this one is GK of x is equal to F of x minus F1 of x minus Fk of x. Now, to check the monotonicity of GK, I can just do like GK of x minus GK plus 1 of x. So you know that if this sequence is negative, it means that we have an increasing sequence. If this difference is negative, it means that we have an increasing sequence. If this difference is positive, it means that we have a decreasing sequence. And if it is equal to 0, it means that we have a constant or a stationary sequence. Now, GK minus GK plus 1 is what? If F1 minus x, F1 of x minus Fk of x minus F1 of x minus Fk plus 1 of x. So what is this? This is F1 of x minus Fk of x minus F1 of x plus fk plus 1 of x. So f1 of x minus f1 of x is 0. So what we have here is fk plus 1 of x minus fk of x. And don't forget that we previously proved that fk, it is a decreasing sequence. If fk is a decreasing sequence, it means that fk plus 1 is less than fk. Fk plus 1 is less than fk. So it means that this one is negative. It's less than 0, since that fk is a decreasing sequence. Now, what do we have? We have gk of x minus gk plus 1 of x less than 0. So this is gk of x less than gk plus 1 of x. Then gk is an increasing sequence. Then gk is an increasing sequence. So the next thing is to compute the limit of gk. So this one is satisfied. We have already this condition which is satisfied, which is very good. We also have which condition? Where is gk? This one is also satisfied because you have to check gk is positive, measurable, increasing, and you also have the limit, and we are done. So the first thing, gk is an increase, it is a positive sequence of measurable functions, and then gk it is an decreasing, it is an increasing sequence. Now, what is the limit of gk? The limit of gk is the limit of f1 of x minus fk of x when k tends to plus infinity, which is f1 of x minus the limit of fk of x when k tends to plus infinity. And we found out that this limit is equal to 0. Don't forget. That is it. We compute fk and fn, they are the same. So we change just the index. So it doesn't matter. So this one is 0. So this limit is f1 of x.
Romaric,
Mm-hmm.
I'm a little bit lost. The question was asking to compute to use the theorem to compute the limit of fn.
Yeah.
But here we are computing the limit of gk.
Yeah. Okay, let me explain.
And you are using inside this formula, you are using what the lecturer asked us to compute.
Yeah. So that is why I thank I don't know the guys who
So me,
mentioned
I'm
that.
a little bit confused.
Yeah, that is why I thank the guys who mentioned this idea, because in the beginning we wanted to apply the Beppo Levi theorem to compute this limit, the limit of the integral of fn, right? That is what we wanted to compute.
Yes.
Now we checked if our function if our sequence fn satisfies the hypothesis of the Beppo Levi theorem, and we found out that the sequence fn does not satisfy that, since that we had a decreasing sequence, right?
Yes.
when we have a decreasing sequence, we cannot apply it. But now we can try to do a transformation. We can try to define a new sequence where we are going to apply the Beppo Levi theorem. And as fk decreased, the idea was to define this new sequence. So the idea, as we have as fk was decreasing, so the new idea was to define a new sequence gk, which is equal to f1 of x minus fk of x. All right. Now you are going to see that this gk satisfy the Beppo Levi theorem. So satisfy the hypothesis. So it means that we can apply the theorem to gk. And if you apply the theorem to gk, it means that you are going to apply the theorem to f1 minus fk. And if you apply the theorem to f1 minus fk, it means that you are going to have the limit of the integral of fk. I don't know if you understand.
Okay, let us proceed.
We introduced this one. We introduced gk because it was impossible to apply the theorem to fk. That is the idea. So each time when you have fk, a decreasing sequence, just think about this idea. So you have to define a new sequence gk. When you
So
define,
our new
yeah,
goal is to find the limit of GK or what?
yeah, the new goal is to find the limit of the integral of gk.
Mm.
When having the limit of the integral of gk, you also have the limit of the integral of fk. You understand? Do you
But we are
understand?
using it already. Like to find the limit of GK, we are using the limit of FK.
No, to find the limit of fk, we are using gk. The limit of the integral of gk, because let's go. Let's come here. I don't know if you understood everything up to this step.
Yes, here we are
Okay.
using the limit of FK inside the definition of the limit of GK, right?
Now let us finish with this. You
Okay.
understand? Now this one is the limit of gk, right? So by the Beppo Levi theorem or by the monotone convergence theorem, we have the limit between 0 and 1 of what? Of the integral, the limit of the integral between 0 and 1 of gk of x dx when k tends to plus infinity is equal to the integral between 0 and 1 of the limit of gk of x dx. I hope that everything is clear up to here. And what is this? This is the integral between 0 and 1 of f1 of x dx. Right? Now, what is the integral? What is this? The integral of gk dx is equal to the integral of f1 of x minus fk of x dx, which is equal to the integral of f1 of x.
Romaric, please.
Yes?
Why didn't you apply the limit of f1 of x? Why didn't you apply the limit
Where?
on f1 of x?
This one?
When you are saying limit of gk of x,
Yeah.
when k goes to plus infinity equal to, you put equal to f1 of x minus the limit of fk of x when k goes to plus infinity. So I'm asking why you didn't apply the limit to f1 of x. Okay,
Yeah.
you did it.
Okay.
But after you
Yeah.
didn't continue
Yeah.
down
Yeah.
the next step. Yeah,
Yeah. What is the index?
you removed the limit on f1 of x. I
Yeah.
don't know why.
We say that k tends to plus infinity, right?
Yes.
This one is 1. It is a constant. Hmm?
Okay.
So the limit is going to be on fk because fk on fk we have
Oh
k.
yes, 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 yes. I understand.
Okay, nice.
Thank you.
Okay, thank you for the exchange. Now, this is the integral. Now, what is the limit of this? The limit of the integral, the limit is linear. So this one is what? The limit of this one. So we don't have k here. So it is this one minus the limit of this quantity. I hope that everything is clear up to here. I hope that is clear. If not, you can ask question, please. I don't know if Anna, Agua, Lex, Asian, Michael, I don't know if everything is good for you.
It's good. But I have question, Romaric, at the bottom, after you put F1 already from F of G of K, why are you computing it again? Like you are substituting F1 minus Fk.
Where here?
Yes, before the last
Yeah.
slide. Like why are you computing it again?
No, I just want to substitute it there. See, I have this result. I have this result, right?
Yeah, you already have F1
Yeah.
in the
So
F1.
now I just want to replace the limit. So this one, what we have on the left hand side. So the limit of the integral of gk by this. I just want to replace by this.
Oh.
I hope you understand.
Okay.
So now I'm going to take this one. I'm going to replace this one by this now. And I will say this one equal to this. That is all. That is what I want to do. I hope you understand. So since the limit of the integral of gk is equal to the integral of f1 of x dx when k tends to plus infinity, it means that the integral, so this one, I'm going to substitute this limit by what we have here. So you have f1 of x dx minus the limit of fk dx when k tends to plus infinity equal to this. Is it okay? So this implies that the limit, so these two terms are going to cancel. So we remain with this one equal to 0.
Romaric,
Yes.
it's like we are doing the same thing since because we already found this one
This limit,
previously.
this limit.
Yes,
Yeah.
yes.
We found it without using the Beppo Levi theorem. Yeah. So that is why I would like to maybe. So I said that we cannot use the Beppo Levi theorem here, but it is like I was wrong. So I can raise it. We cannot use the Beppo Levi theorem to this function to fk. We cannot use the Beppo Levi theorem to fk, but it doesn't mean that we cannot compute the limit of the integral of fk without using the Beppo Levi theorem. We can still use the Beppo Levi theorem to compute the limit of the integral of fk. But to do that, we need to do a transformation. Since that fk is a decreasing sequence, we can call a new sequence gk, which is equal to f1 of x minus fk of x, this new sequence. And by using this new sequence, by the end of the day, we are going to have the limit of the integral of fk. So normally, maybe I can erase this part. And I think that it's the same thing that we did last time. And today, thank you that our classmate was there to help us. So maybe I'm going to erase this because it can confuse you. Because it is better to move directly to GK. So when you found that Fn is a decreasing sequence, so now you can move directly to GK. I don't know if you understand the idea of the lecture. So I'm going to remove this thing.
This is just a confusion from you.
Yeah, that is why.
But
Let
I
me.
think I understand. It's fine.
I will explain again everything. Let me remove this part. Let me remove this. Okay. Let me come back as fast as possible. Short. Okay. I was trying to put everything together to avoid confusion. Now, okay, let us come back again here. So this was the question. The question was to compute the limit of Fn by using the Beppo Levi theorem, right? I hope that everyone is there and everyone is there.
Yeah, here.
Okay, so the goal was to compute this limit by using the Beppo Levi theorem. Now, it was impossible to apply the Beppo Levi theorem to Fn of x, since that Fn it is a decreasing sequence of measurable functions. And we know that if you have a decreasing sequence of measurable functions, we cannot apply the Beppo Levi theorem. Now, what we need to do is to construct or to build an increasing sequence of function, such that with that increasing function, we'll be able to apply the Beppo Levi theorem, and by the end of the day, we are going to have also the limit of this integral. That is the goal. So that is why as Fn was decreasing, we decided to create a new function jk, which is equal to f1 of x minus fk of x. Now, we have to check if jk satisfies the hypothesis of the Beppo Levi theorem. And how to do that? We have to check that jk is positive. We have to check that jk is measurable. Of course, jk is measurable because jk is equal to fn to f1 minus fk. And f1 and fk are all measurable. And we know that the sum of two measurable functions is measurable. Now, we don't know if this one is positive, because it was possible also to take fk minus f1, but we decided to take f1 minus fk. Why taking f1 minus fk? Is because we know that fk decrease. When fk decrease, it means that fk, which is the highest term, is less than fk minus 1, fk minus 2, up to f1. So it means that fk is less than f1. So if fk is less than f1, it means that f1 is greater than fk. And if f1 is greater than fk, this means that f1 minus fk is greater than 0. And if f1 minus fk is greater than 0, it means that jk is greater than 0. So we are done with the first hypothesis. So our sequence GK is measurable. It is a positive sequence. Now the second thing that we have to check is the monotonicity. So we have to check that JK, it is an increasing sequence compared to FK, which was a decreased sequence. So now JK is an increasing sequence compared to FK, who was a decreasing sequence. How to show it? We know that JK plus 1 is F1 of, if F1 minus FK plus 1, and JK is F1 minus FK. We just have to compute the difference between JK and JK plus 1. And if this difference is less than 0, we conclude that JK is increasing. So JK minus JK plus 1, if it is equal to F1 minus FK, minus in the parentheses F1 minus FK plus 1. So we just have to substitute. And by the end, we are going to have that JK minus JK plus 1 is equal to FK plus 1 minus FK. And don't forget that FK is a decreasing sequence. So it means that FK plus 1 is less than FK. So if FK plus 1 is less than FK, it means that FK plus 1 minus FK is less than 0. And if FK plus 1 minus FK is less than 0, it means that JK minus JK plus 1 is less than 0. Then JK is an increasing sequence. So if JK is an increasing sequence, JK, it is a sequence of measurable function, positive. It means that we can apply the convergence, the monotone convergence theorem, which is the Beppo Levi theorem, to JK. And prior to that, we need to compute the limit of JK, because don't forget that we need to use a limit in the theorem. So what is the limit of JK? So the limit of JK is just the limit of F1 minus FK. And we know that F1, it's a constant. So the limit of JK is just F1 minus the limit of FK. And as we know, we computed the limit of FK, and the limit of FK was 0. So that is why that the limit of JK is just F1. So we have the limit of JK, which is F1. We have JK, which is an increasing sequence. We have JK, which is measurable. We have JK, which is positive. Then we can apply the Beppo Levi theorem. So it means that if we apply the Beppo Levi theorem to JK, it means that the limit of the integral of JK is equal to the integral of the limit of JK. So because the Beppo Levi theorem allows us to switch the position of the integral and the limit. So we are going to switch the position. We are going to put now the limit inside the integral. So it means that the limit can enter inside the integral. Then the limit of JK is now, the limit of the integral of JK is now the integral of the limit. And the limit of JK has to be computed if it is F1. Then we have this. Now what we need to do is to find this one, the limit of the integral. To do that, what is the integral? The integral of JK from 0 to 1 is what? We replace just JK by the expression that we set in the beginning. JK was equal to F1 minus FK. So the integral of JK is now the integral of F1 minus FK. Don't forget what we need. You need to have the limit of the integral by the end of the day. The limit of the integral of FK. Then the integral is linear. So the integral of F1 minus FK is the integral of F1 minus the integral of FK. Now I can put the limit. If I put a limit here, I will have the limit of the integral equal to this. So this quantity is a constant. So I just put it here. Minus the limit of the integral of what we are looking for since the beginning. So we are looking for the limit of this one. And we are using the Beppo Levi theorem. But we are not using the Beppo Levi theorem to FK, because FK is decreasing. Now we are using the Beppo Levi theorem to JK. And by using the Beppo Levi theorem to JK, we are going to have the limit of the integral of FK by still using the Beppo Levi theorem. So you understand how the Beppo Levi theorem is important on how it appears. Then you have this. What you need to do is now, as you have this one equal to this one, and since this one is equal to this one, it means that this one equal to this one. So this one equal to this. That is what I called. Since this one equal to this one, I just have to replace this limit, the left hand side by this quantity on the right hand side equal to this. Then this quantity is going to cancel with this quantity. Then it will remain just minus the limit of the integral of fk equal to 0. Then we have this one, the result. I don't know if you understood now the algebra. I don't know. Have you understood? I don't know. Maybe people were lost.
Yeah, it's
Please,
fine.
can you scroll up? Please, can you scroll up a little bit? No, it's okay. Where you did this, which one? You said the limit of GK is just equal to the limit of F1.
Yeah, since that this is where we computed. This is the limit of JK. The limit of JK of X is equal to the limit of F1 minus the limit of FK, right? The limit of JK is equal to the limit of F1 minus the limit of JK. Since that JK is equal to F1 minus FK, JK is equal to F1 minus FK. It means that the limit of JK is the limit of F1 minus FK. Now, F1 does not depend on K. So it means that the limit of F1 is still F1. Now, this one is minus now the limit of Fk. And the limit of Fk was equal to 0. Right?
We did that upward.
Yeah. So it means that the limit of Jk is just F1. So the limit of Jk is just F1. So that is why we replace here the limit of Jk by F1. I don't know if you are still confused or it is okay.
It's okay. Thank you.
Okay. Bervian, have you understood very well? Anna Hajwa
Yeah, it's fine for us.
for you. Anita,
I understood.
okay, nice.
Okay.
Okay. So it is good for this subject. So we are going to do the last one, the last subject. So I think that maybe you can go and correct what we previously did last time. So what we did the last time. We still have two subjects or one subject. Okay, we still have one. So the last one. Thank you again for the idea that you help us with that. Now, functional analysis. Functional analysis. Academy oh Academy 2024, 2025. Academy 2024, 2025. It's the session of 17th of February 2025. So the first question, as you know, it seems to be the same thing. I don't know if we are not going to do it again. So we have omega, a subset of Rg, be a measurable set, and Fn, so measurable, set, Fn from omega to R, a sequence of measurable functions. So the first question is to define the LP, define LP space and his norm. We are not going to do it because we previously did it. And what means for Fn to converge in LP already, and convergence in LP already. Now the second question is, if we consider omega, if we consider omega equal to R and the sequence of measurable function Fn defined as follow: Fn of x equal to 1 if x is between 1 over n plus 2 and n over n plus 1 and 0 otherwise. So the first question is to check the almost convergence and determine the limit. So let us check if Fn converge almost everywhere and determine the limit function f. Determine the limit function f. So as you know, this question is very easy. What is the limit of Fn of x has n tend to plus infinity? So this one is 1 here. If what? So when n tends to plus infinity, what are you going to have in the interval? So you know how to do. So we are all together. We all know that this one will be 0, 1 and 0 otherwise. then Fn converge almost everywhere to f of x equal to 1 if x is between 0 and 1 and 0 otherwise. So let us find for which values of p in 1 plus infinity such that Fn converge to f in LP of R. So this one is the same exercise. I don't even know the difference. So if you take the limit when n tends to plus infinity of the integral of Fn of x minus fx power p dx equal to 0. So this one is the limit when n tends to plus infinity of the integral between 1 over n plus 2 n over n plus 1 of 1 minus 1.
Please, homework.
Yes.
Please, how did you obtain the bond of x when you were computing the limit?
Yeah, if I just take this interval, what is the limit of 1 over n plus 2?
When n goes to plus infinity, 0.
What is the limit of n over n plus 1?
Yeah, that's my problem. Oh, okay, it's 1. Okay, it's 1. Thank you.
Thanks. So we can see that for any value of p, this one is still equal to 0. So it's better to put this like this. So whatever the value of p. So for all p, Fn converge to f in LP. Now we are going to move to the second question, which is very interesting because we are going to use a new concept, the dominated convergence theorem. So the second question, the first item is to state the dominated convergence theorem. So let us state the dominated convergence theorem. Let us state the dominated convergence theorem. Now, it is the same thing like the monotone convergence theorem, such that except that we are going to use a new notion of what we call integrability. So let Fk from Rg to minus infinity plus infinity be a sequence of measurables function. So you can understand, you can notice that there's a difference here. With the dominated convergence theorem, we don't only need positive sequence or positive functions. So we can also have negative, positive, whatever. So that is why you can see f goes from rg to minus infinity to plus infinity. So let's fk be a sequence of measurable functions. Now, suppose or assume that there exists a measurable functions f from rg to minus infinity plus infinity, such that fk converge almost everywhere to f. Secondly, suppose that there exists a summable function or an integrable function. Summable means to be integrable. Integrable means to be L1. So the integral of the absolute value of the function is finite. So suppose that there exists a summable functions j from rg to 0 plus infinity. So your j is supposed to be positive now. So you have to suppose that there is a summable function. So it is positive, such that the absolute value of the sequence fn of x is less than gx for almost every x. So when you have these two hypotheses, you are done. So when you have a sequence of measurable functions and you can find a function f such that fk converge almost everywhere to f, and you can also find a summable function such that the absolute value of the sequence that you have is less than that summable function, then the limit of the integral of fn when n tends to plus infinity is equal to the integral of the limit, or it is equal to the integral of fx dx. So the dominated convergence theorem and the Beppo Levi theorem, they have the same conclusion. So we are using those theorems to have the same result. So you have to check, maybe given a function that you have, if you cannot show that your function it is an increasing sequence or it's a decreasing sequence. So if you cannot have the monotonicity of your sequence, maybe you're in the case that the monotonicity is very difficult to find, or maybe your function is very robust. So it is better for you to use the dominated convergence theorem. So you understand?
Can you come again?
I see that this one, for the dominated convergence theorem, we don't need the monotonicity. So we don't need that fk should be increased or decreased. So if you have maybe a sequence of measurable functions and you are looking for the limit of the integral of that sequence, it could be very difficult for you to look for the monotonicities. So it is better for you to check if you can use the dominated convergence theorem. And to use the dominated convergence theorem, you just need to find this f such that your function is going to their sequence will converge almost everywhere to f. And you also have to find the summable function such that the absolute value of your sequence is going to be less than the summable function. So this theorem is there to avoid the notion of increasing, decreasing, so to avoid the notion of monotonicity. I hope that it is good for you. Is it good for you?
Yes, please.
Okay, nice. Now, consider Fn from 0, 1 to R. So with n given, so with n an integer. And the sequence is given by Fn of x equal to n sine of nx over n squared plus 1. So let us use the dominated convergence theorem. The dominated convergence theorem to compute the following limit. So the limit of the integral of Fn of x dx when n tends to plus infinity. Okay, let us use this now. So what we know is that the sequence of function is continuous. And if the sequence of function is continuous, it means that it is measurable. So Fn is measurable. Now, we can check at the limit also. What is the limit of Fn of x when n tends to plus infinity? What is the limit according to you?
F.
What? You have to know how to compute the limit. Zero. I don't think that it is zero. And maybe it is zero, but for me, it is like the limit, it is x. It seems to be x. Don't forget that you have n on the sine function. So let us do it like this. We are going to do it on a better way. Maybe someone has another better way. So if I take maybe capital N equal to 1 over n. It's because I want to go in 0. So this implies that when n tends to plus infinity, capital N tends to 0. So it means that the limit of fn of x when n tends to plus infinity is equal to the limit of capital N when capital N tends to 0 of 1 over n sine of x over n over 1 over n squared plus 1. I hope that we are all together. I hope. So this is the limit of what? This is the limit of n squared sine x over n over n times over n squared plus 1. I hope that you understand. So this one is the limit of n sine x over n over n squared plus 1 when n tends to 0. Right? Are we together?
Yes.
Oh, okay, nice. I'm happy to know that we are together. Okay. Now, what is this limit when n tends to 0? It is like the gas was right. It is 0. I don't even know why I did this. It's still 0. I was thinking that it was x. It is 0. So it is 0. So let us show why it is 0. I wanted to use the Taylor expansion, but we don't need to use it. So now we can just, we know that the sine is sine of nx is between, right? We know it. Now this quantity is positive. N over n squared plus 1 is positive. I'm still doing a mistake. Yeah, I'm not doing a mistake. We are all together, right? Now the limit when n tends to plus infinity is less than the limit of fn of x, which is less than the limit of when n tends to plus infinity. So this is equal to what? We have 0 here. We have 0 here. Then the limit of is 0, as the guy said. Thanks. Thank you. Now, what is the absolute value of fn of x? What can we say about the absolute value of fn of x? So we have n here sine of nx over n squared plus 1. So this is less than n over n squared plus 1, less than sine of nx. So now, according to me, I know that sine is ellipsis it is an ellipsis continuous function. So I can say that this one is less than nx. So you have n squared absolute value of x. X is positive here, so the absolute value of x is x. So this is less than x, since that n squared over n squared plus 1 is less than 1. Now, this is our j. This is the j. And you have to check if this j is measurable. And you have to know that this j should not depend on n. It could be 1. It could be a function of x, a constant function, but not a function which depend on x, which depend on n. So what is the integral of this? That is to check that f is summable. So if this integral is finite, you just conclude that it is summable. So x, which is our j, is summable. Then by the dominated convergence theorem, the limit of the integral of fn dx when n tends to plus infinity is equal to the integral of fx dx, and fx is 0. So this is fx, don't forget. I don't know if you have any question. Do you have any question related to this question? No question? Anna, Asian, adios. Meridian, if everything is okay. Michael, I don't know if everything is okay for everyone.
For me, it's okay.
Okay, nice. So if it is okay for everyone, we are going to end the session because this was the last question of this subject related to the functional analysis part. Thank you very much for people who attended this session.
Thank you to you too. Please don't forget to upload the PDF.
Yeah, of course. I'm going to send you the PDF, and I'm going to forward the YouTube link with you.
Okay, thank you.
Nice. Thank you. See you.